thank you. I want to start with the question, what is the color of Earth? And I guess many of you will say blue, and that makes sense because after all, 70% of Earth's surface are covered by water. So that answer seems correct, but it's actually not correct because a tiny part of that water is actually inside the atmosphere where it forms clouds. And clouds are very powerful in reflecting sunlight. And so actually maybe the answer to that question is blue and white. So in this talk I will a lot talk about clouds. So clouds are important to how climate is today. Climate would be very different if clouds were not present on Earth, but clouds are very important about climate change and how the regional climate will respond to global warming. So for us here in Vienna, the main vehicle of regional climate change is actually atmospheric wind patterns, the wind pattern that we call the jet stream. You might have experienced it by being on a plane, and you know that planes go much faster from west to east than from east to west. So the jet stream is a band of very strong winds somewhere across the Atlantic at a height of about 10 kilometers or so. And it's also important because it guides the low pressure and high pressure systems that travel across the Atlantic and that really shape our everyday weather. So these weather systems we call cycle-on cyclones. And so they really ride along the jet stream, and some of them can bring very intense wind, very intense precipitation. So many of the extreme events that we have experienced in the past have been associated with cyclones. So understanding how the jet evolves and how the cyclones evolve is a major topic in climate change. An example is here the recent flooding, well not so recent, the historic flooding of southern parts of England in the winter of 2013-2014. There was a very strong straight jet across the Atlantic that brought cyclone after cyclone to the British Isles. But it's also important to realize that the jet stream is tightly coupled to clouds. And you can see that coupling on maps like these. On the left-hand side you see the jet stream. On the right-hand side you see clouds. And you see how the clouds make the jet and the cyclones visible and really organize along the jet stream. So clouds and the jet couple on scales that we call planetary, many thousands of kilometers. But clouds themselves are turbulent phenomena, so they are the result of upward motion, of convection, of thunderstorms. So they organize also on scales of maybe a few meters and kilometers. But they also have an aspect that lives on much, much smaller scales. Namely, the cloud is always a collection of individual particles. And this can be liquid droplets, or it can be ice crystals. And these crystals in particular can be very, very complex. They can have very different shapes. They can have these rosette shapes, column shapes. And the shapes of these ice crystals actually has a lot of impact on how the cloud behaves and how it couples to the jet. And this is what we are trying to do in my research team here in Vienna. So trying to both understand clouds on one hand and jet on the other hand, but really also how the two work together to shape regional climate where we live here, and also how regional climate will respond to global warming. So we do this from a theoretical perspective and from a modeling perspective. So the good news is that we know, to a large extent, we know the equations that govern the atmosphere. This is physics, so we know these partial differential equations. The bad news is these are very nonlinear, multi-scale equations. It's very hard, if not impossible, to solve them analytically. So what we do is we turn to computers. So we put these equations into a numerical form that's handleable by computers. And that's nice because, well, it gives us the opportunity to experiment with the Earth system, which otherwise would not be possible. And so we run experiments and try to learn about how the climate works. And I want to give you 3 examples of what we are doing. The first example is we can pretend we would live in a world where we can just prescribe clouds. So we can lock clouds to a particular climate state. Of course, it's not possible. That will not happen on real Earth. But it's a very drastic intervention into these models that allow us to understand, well, how do cloud feedbacks play out under climate change? What is the role of cloud changes, for example, for the climate change response of the jet stream? Another example is we can take these models and try to simulate Earth as realistically as possible, but we can also take these models in more idealized setups. for example, an aquaplanet. It's just water at the surface, there's no continents, but there's plenty of clouds up in the atmosphere. And that helps us to tease out some of the basic mechanisms which are at play here. And the third example I want to give you is, well, in the climate science community, we are living in very exciting times because we're actually changing the way we are modeling and thinking about the climate system. So we're leaping into an era of completely new models that we call global storm resolving models that can simulate the Earth system at spatial resolutions of 1 kilometer, and that allow us to create what we call digital twins of the Earth system. So a digital twin model is a model that looks about right, like Earth, but of course it's not Earth, it's still a model. But it has many features, like extreme events that we care about in terms of climate change. Of course, just to convince you of the powerful aspect of such digital twin models, on the left-hand side you see such a model. On the right-hand side you see the same day from observations from satellite. So I think this is really an astounding, striking similarity that we are going to explore in the coming decade or so. To run these models, we turn to supercomputers. And so we take these models and we run them on hundreds of thousands of compute cores. And that's really a remarkable scientific and technological achievement. But it also produces a problem because you can run these models at very high resolution. You get a data point every kilometer, which means these models just turn out data and data and data, so you produce petabytes after petabytes very easily. So it also challenges us to think about how we work, how we analyze data, and funny enough, we turn to, for example, cloud computing to understand clouds. So with this, I would like to close, and hopefully I could show you a little bit of how important clouds are in the climate system. I believe you cannot understand the climate system without understanding clouds. The challenges that come with clouds, the many scales, and also a little bit of the excitement that comes with studying them. Thanks.